In this video, we're going to talk about some applications of logarithm. So we'll look into how logarithm is applied in today's world, and we'll discuss them in detail to an extent. So let's get started. So the first example I'm going to discuss is the use of logarithm to simplify calculation. Actually, logarithm was initially invented in 1614 to simplify computation or calculation. So that was the actual intention of the invention of logarithm. So I'm going to discuss what we mean by simplification of calculations. Like what exactly do scientists or mathematicians mean when they say, oh, we use logarithm for that purpose? So the first thing is those years or those eras, we had no calculators, we had no computers, so there was no way to calculate very complex or very tough computation without using some tools like logarithm. So let me just give you an example. Let's say you are asked without calculator to look for the cube root of 450, right? So how would you have gone about it? You don't have any calculator, and how would you have gone about this? So what they did in those areas was this: they came up with what they call table of logs. So a table of logs would have logarithms of numbers like 2, 3, 4, and so on. And with those tables, mathematicians were able to calculate almost any type of numbers with high level of precision. So how was that possible, and how can we also apply it in today's world? So I'm going to use this example as an illustration to show you how the how logarithm can be used to simplify computations. So let's look at this. So imagine you have your log table, and in your log table you have the following. From your log table, you know that log 2 to base 10 is 0.3010, and log 3 to base 10 is 0.4771. So given that these two are known from your log table, right? So the question is, what's the cube root of 450? Now, the first thing I want to do is to equate this number to x, or we can say x equals to this. So we are looking for the value of x, right? So let's try to apply log on both sides to base 10. So we have log of x to base 10, and we have log of the cube root of 450 to base 10. So what we want to do now is to try to write this in a simpler form. So this is 450 raised to the power of 1 over 3. From the law of indices, you can write this cube root as 450 raised to the power of 1 over 3. And here we have to base 10. Now, we can take this 1 over 3 to the back. That becomes 1 over 3. Then log 450 to base 10. So the next thing we can do is we can break down 450 into this 45 times 10, and we can break down this 45 as 9 times 5 times 10, and we can go further by breaking this down to we can break this down to 3 raised to the power of 2 times 5 times 10. So what else can we do here? We can express the 5 as 10 over 2 times 10. So it becomes 3 raised to the power 2 over 2 times 100. So this is how we can express 450 in terms of 10s, 3, and 2. So you will see why we are looking at expressing in terms of 3, 2, and 10 is because we know from our table we know the logs of 2, we know the logs of 3. So these are the information given to you. So now what's the next phase? The next phase is to just plug that in. So we just take this as log 3 raised to the power 2 over 2 times 100, then to base 10. Then the next phase is to take 1 over 3 and we spread everything out. So spreading out means we take log 3 to base 3 raised to the power 2 to base 2. Since it's times divided by 2, that means minus log 2 to base 10. Sorry, this is to base 10. Then plus log 100 to base 10. So I'm going to go to the next page. So from the previous page, we have x log x to base 10 equals 1 over 3 log 3 raised to the power 2 to base 10 minus log 2 to base 10 plus log 100 to base 10. So what we can do here is we can bring this 2 down. So this becomes 1 over 3 into bracket 2 log 3 to base 10 minus log 2 to base 10, then plus log 10 to base 10 raised to the power 2 to base 10. Then we can simplify further as follows: 2 log 3 to base 10 minus log 2 to base 10 plus 2 log 10 to base 10. So what I've just done basically is to rewrite this roots, log of roots, cube root of 450 in terms of this. So log of this in terms of all of this. So now we can substitute the values we know for log 3. This is log 3 to base 10. So we know that from the table. So the way mathematicians do this is this: they already have a table that gives them log of certain key numbers. So with those information, they try to compute a lot of mathematical calculations using those tables. So that's what I'm trying to demonstrate here. So now we know from our table that log 3 to base 10 is 0.4771. Now we know log 2 to base 10 is 0.3010. Then log 10 to base 10 is 1 based on the laws of logarithm. So now we can simplify further by just doing basic calculation. So that becomes 1 over 3. Then we have 2 times 0.4771. So that will give us, this will give us 0.9. Okay, this 2, this is 4, and this is 5. So minus 0.3010 plus 2. So eventually I'm going to get the following, which is 2.6532. If you divide by 3, you are going to get 0.8844. So this is log x to base 10 equals 0.8844. So the next thing those mathematicians will do is to look for the anti-log. So they take the anti-log of 0.8844. If you take the anti-log of this, that will give you x. So the anti-log of this is like saying what should be is more or less like looking for 10 raised to the power of 0.8844. So that's what the anti-log of 0.8844 is all about. So they also have a table for anti-log. So if you look at the anti-log table of 0.8844, the answer will be equal to 7.663. So we can say that the cube root of 450 is equal to 7.663. So that's exactly how this kind of calculation would have been done in the 17th or 18th century. So So one application of logarithm is to simplify calculations, either very complex calculation or calculation involving cubes and roots and so on. So that's one application of logarithm. So let's take a look at the other application of logarithm. The second application of logarithm is especially in the world of computer science is the estimation estimation of the computational complexity, or you can call it in a simpler form, computational time of binary search. So you can use logarithm to compute how long it will take to search a sorted list. So before I go into exactly how we use logarithm to estimate that in programming, like in computer programming, let me explain this key concept, which is binary search. So what is binary search? Then how do we estimate the time it would take, or how many checks we're going to carry out before we can figure out the position of anything? So let's talk about binary search. I'm going to talk about binary search in terms of this information provided in this table. So imagine in a particular class where we have 16 students. So let me give you this scenario. So pay attention to this. You have a classroom, and in that classroom, you have 16 students. And in that classroom, the class teacher has a list of all the students with their score. So in this case, Mike scored 92 and the position of Mike is 1. Helen scored 90 and our position is 2, and the list goes on, right? So this is what we call a sorted list. A sorted list is a kind of list where the names are arranged in order, either ascending or descending order. But in this case, it is in descending order. The score is in descending order. So now here is the question that the teacher is throwing to each of the students. Think about it this way. If you happen to be a student in the class and you know your score, right? But you don't know the score of your friend, you don't know the score of your classmate, and the teacher asked you, can you guess your position? Let's imagine you don't know your position, but you know your score. So let's imagine you happen to be Steve. Steve got 10, right? I mean, Steve's position is position 10, which means, and the score is 60. Now imagine you happen to be Steve. You don't know your classmate's score. You don't know their rank. You just know your own score. And you don't know your position. You know your score. You know just your score. You don't know your friends, your classmates' score, and you don't know your position. And now the teacher wants to play a game. Now the game is you are to guess your score. So the game is guess your score. That's the game, right? So now, if you want to guess your score, the most naive way to guess your score will be to just keep guessing from 1 to 16 because you're 16, right? So which means your score, your rank is from 1 to 16. So I could just keep guessing like 1, 2, 3, 4, 5, and the teacher will just tell me yes or no, right? So let's say the rule of the game is this. You guess a score and the teacher will tell you no. But if the teacher tells you no, the teacher will also tell you the score in that position you just guessed. So let's say I guess that, oh, my position is position 2. Now, in that case, Steve is not position 2. So the teacher will say, no, that's not your position. And the teacher will tell you that in that position, the score of that person is 90. That's the score. Now, the question I'm throwing at you is, what is the smartest way to guess that will minimize your number of guesses? That is, how would you guess in such a way that you will not you will not get so much before you arrive at the answer? So, as I said earlier, the most naive way to guess is just to move from 1 to 16. So, if you do that, in the worst case scenario, you will guess 16 times because if you happen to be Dupe, for instance, When you say position one to be no, position two will be no, up to 16. So when you get to 16, the teacher will say, yes, that's your position. So it means if you guess in a naive way, in the worst case, you will make 16 guesses. In the worst case, that's the worst case for everybody, right? So, but then computer scientists they figured out a smarter way to guess, to figure this out without necessarily going through the whole system. In fact, if you apply this concept called binary search that I'm going to explain, you will not guess more than 4 times before getting anybody's score. That is, irrespective of your score, you won't guess more than 4 times to figure out the answer. So I'm going to explain to you how I got to know that the worst case number of guesses will be 4. How did I get to know that the worst case is 4? So that is what logarithm can help you figure out. But before I explain how I came across 4, let me explain what binary search is. So now let's play this game. So now I happen to be Steve and I want to use binary search to guess my rank. I know my score, but I want to guess my rank, right? So what do? I can guess between 1 to 16, right? That's my guess range. I can guess anything from 1 to 16. If you want to guess smartly, the first using binary search, as the name implies binary, you split the search into half. Then you guess what is at the middle. You guess 8. You don't just guess 1, 2, or random. Just guess, tell the teacher that your position is 8. So I'm going to tell the teacher, oh, my position is position 8. Now let's take a look at position 8, right? Position 8 has what score? Position 8 has 65. Note that my score is 60. I am Steve, right? My score is 60. And I told the teacher that, oh, I guess my position is position 8. Now, the teacher will tell me no, that position 8 is not my position. And the teacher will also tell me that the score at position 8 is 58, 50, 65 rather. Now, what next should I do? Balancer tells you to now make the next guess, but to make the next guess, you will have to eliminate one side of your search space, of your search range. Now, if my score is 60 and position 8 is 65, what this implies is my score should be within this position because 65 is greater than 60. So, which means my score, sorry, it means you should eliminate this zone rather. So, your score should be within this range because when you move up the rank, your score drops. What that means is any position from 1 to 8 implies higher score. So some with position 1 obviously is higher than, we have a higher score than 65. So since my score is less than 65, it means I have a lower rank. That's what it implies. It means I have a lower rank. So now what do we do here? What we do is we eliminate the range that is no longer feasible. Mind you, I've only made one guess, and by making one guess, I've reduced my rank range to 8 and 16, between 8 and 16, right? I've reduced it to a number between 8 and 16. So this is where I should be looking for. I shouldn't bother about 1 to um, uh, 7. So now, what next do? We look at the midpoint of this. So if you take a look at the midpoint of 8 and 16, more or less like you, to get the midpoint, you just add them up and you divide by 2, and that will give you 24 divided by 2, and that's 12. So we are going to guess 12. So I'm going to tell the teacher that, oh, my position is 12. That's the next guess I'm going to make. So this is my second guess, right? But then the teacher will tell me, oh, 12 is not your position because the score is 56. Now, what do I do next? Should I eliminate this zone or this zone? Think about it. If you anything from 8 to 12 implies score from 65 to 56. Anything from 12 to 16 implies 56 or less. Since my score is between 65 and 56, it means I'm going to eliminate the zone. So I'm going to reduce my guessing zone to 12 and 8 to 12, right? So now what do I do next? I just do the same thing. I just add them up. 8 plus 12, that's 20. Divide by 2, that gives me 10. Now I'm going to guess 10. By the time I guess 10, the teacher will say, yes, correct, because that is your position. So think about it. I've just made three guesses. I guessed 8, 12, and 10, and I got it at the third guess. Now, this style of guessing, where you guess the middle of your guess range, where you guess the middle, is called binary search. So the idea is you don't just guess um, in ascending order like one, two. If I had guessed in a naive way, that is, if I have guessed one, two, three, four up to 10, I would have guessed up 10 times before reaching out my answer. So, which means if you use binary search, you are guaranteed to guess less in the worst case scenario. So, what I mean by worst case scenario is if it turns out that I happen to be at number 16, I will guess just four times. So if you try to do if you try to walk through this, the case of 60 using the same method, you will see that you will not guess more than four times before reaching the right answer. So now the question now is, how did I arrive at four? So in computer science, we estimate the number of guesses as follows. We take log of the number of items to base 2. So this is the maximum guess that will be made. The maximum guess or guesses that will be made before you figure out the right position. So in this case, n in our case, the number of students here is 16. And if you solve for this, you get log 2 raised to the power 4, which is 4 log 2 to base 2, and which gives you 4. So this is how computer scientists estimate how long it takes or it will take for a given a query to be obtained within a sorted list. You may be wondering, how powerful is this binary search? Binary search is extremely powerful in the world of computer because imagine you have a billion user or 10 billion user. Binary search can help you estimate, can help you search for queries in a very, very short amount of time compared to just randomly guessing. So let me give you an example. So let's say you have n, which happens to be, let's say, um, let's say we have 100 billion, 100 billion users, right, or items. Now, imagine in the worst case where the item is at the very bottom. It means you are going to make 100 billion guesses, or you're going to search up to 100 billion items before reaching out the answer. But if you use binary search approach, in the worst case scenario, you are going to make the following guesses, or you are going to check just log n to base 2 items before reaching out the right uh, query or the right position. So what this implies is instead of 100 billion checks, you are only going to check log 10 raised to the power of this 6. This is 333 and 2. So that's 9 with 2. That's 11. So if you do this math, that's 11 times log 10 to base 2. That will give you 11 times 3.32, and that will give you roughly 36.54. Roughly this figure, that's what you're going to get. So what I've just done is this. I've just shown that instead of you making 100 billion queries, with binary search, you just make a maximum of, in the worst case, a maximum of 36.5, which is roughly, you can just approximately 37 checks before reaching out any position, before figuring out the position of any score. So the point here is there's a very powerful technique that is used in the real world to quickly search for items in a very, very large list. So this is a very practical application of logarithm. Although the logarithm is not exactly what helps you figure out the set, the logarithm helps computer scientists to estimate how long, in the worst case, that such search would take. So that's a very interesting application of logarithm.